In this lecture, we apply Möbius transformations and the cross ratio of complex numbers to prove Ptolemy's theorem. Let z1, z2, z3, and z4 be the vertices of a quadrilateral as shown in the diagram. Ptolemy's theorem states that the four vertices all lie on a circle if and only if the product of the lengths of one pair of opposite sides plus the product of the lengths of the other pair of opposite sides equals the product of the lengths of the diagonals, or the product of the absolute values of z1 minus z2 and z3 minus z4, plus the product of the absolute values of z1 minus z4 and z2 minus z3 equals the product of the absolute values of z1 minus z3 and z2 minus z4. Ptolemy's theorem is a biconditional statement, so that there are two statements or directions that we must prove. For the first statement or direction, we assume that the quadrilateral is inscribed in the circle, or that the four vertices of the quadrilateral lie on the circle. Then we prove that the equation of the absolute values is true. For the second direction, we assume that the equation of the absolute values is true. Then we show that the vertices lie on the circle. So for the first part of this exercise, we assume that z1, z2, z3, and z4 all lie on a circle. Without loss of generality, we choose the arguments of z1, z2, z3, and z4 such that the argument of z1 is 0, which is less than the argument of z2, which is less than the argument of z3, which is less than the argument of z4, which we set less than 2 pi. We divide both sides of the equation of the absolute values by the right side, or the absolute value of z1 minus z3, times the absolute value of z2 minus z4, and we must show that the left side is equal to 1. So we work on the left side of the equation. In some of the absolute values, we have also rearranged the indices without changing the value of the absolute values. This expression without the absolute values is what is often referred to as the complex cross ratio of z1, z4, z2, and z3. The cross ratio of the complex numbers w1, w2, w3, and w4 is given by this formula. So the second quantity is the absolute value of the cross ratio of z1, z2, z4, and z3. To prove the first direction, we need to show that this sum is equal to 1. To help us achieve this goal, we apply the unique Möbius transformation that we call m of z, where m of z1 is 0, m of z2 is 1, and m of z3 is infinity. We regard minus infinity and infinity as the same point infinity on the extended real line. M of z is actually equal to the cross ratio of z, z2, z1, and z3, and is given by this formula. We do not know exactly where m sends z4, so we'll just call m of z4 zeta, where zeta equals x plus y times I, where x and y are real numbers, and I equals the square root of minus 1. Möbius transformations map an isocline which is either a circle or a line in a one-to-one fashion onto another isocline which again is either a circle or a line. Therefore, zeta must be on the same isocline that passes through 0, 1, and infinity, the isocline onto which m maps the circle. That isocline is the real axis which 0 and 1 determine, and on which infinity also lies, so that zeta must also be a real number, so that y must be 0, and zeta is equal to x. Cross ratios are invariant under Möbius transformations, which means that the first cross ratio equals the cross ratio of m of z1 or 0, m of z4 or zeta or x, m of z2 or 1, and m of z3 or infinity. So this first quantity is equal to 1 over the absolute value of 0 minus infinity times the absolute value of x minus infinity over the absolute value of x minus 1. We interpret the absolute value of x minus infinity over the absolute value of 0 minus infinity as the limit of the absolute value of x minus z over the absolute value of 0 minus z as z tends to infinity. That limit is 1, so this part of the left side is equal to this quantity. We do something similar for the second cross ratio. So the second part of the left side is equal to the absolute value of 0 minus x over the absolute value of 0 minus infinity times the absolute value of 1 minus infinity over the absolute value of 1 minus x. The fraction involving infinity has limit 1, so that the second part of the left side equals the absolute value of x over the absolute value of 1 minus x. At this point, we do a little sidetrack and talk about some pertinent information about Möbius transformations. Every Möbius transformation can be expressed in the form the quantity az plus b over the quantity cz plus d, where a, b, c, and d are complex numbers, and ad minus bc is non-zero. We can rewrite this in this form if c is non-zero, or if c is 0 in this form. Now, every Möbius transformation is the composition of a dilation/contraction, a rotation, a translation, and the reciprocal map W equals 1 over z. Take this form for example. We have multiplication by a complex number, which is a dilation/contraction composed with a rotation. Addition of a complex number is a translation. This is the reciprocal map. We have another dilation/contraction composed with a rotation. And we have another translation. Every one of these transformations is a Möbius transformation that maps an isocline onto another isocline in a unidirectional way. What we mean by this is that if we trace the graph of an isocline in one direction, correspondingly the Möbius transformation traces the image isocline in a single direction, as in the case of a dilation/contraction, a rotation, a translation, and the reciprocal map. A Möbius transformation, being the composition of a finite number of these transformations, will not double back or backtrack on the image isocline. So on the circle starting at z1, then to z2, then to z3, M should trace the path from M of z1 or 0 to M of z2 or 1, continue along this direction to M of z3 or infinity to the right. z4 is in the opposite direction from z1 along the circle. Correspondingly, M of z4 should be in the direction opposite the one from M of z1 to M of z2 on the real line. Therefore, M of z4, which is zeta, which is equal to x, must be less than 0. So 1 minus x is positive, so that the absolute values of x minus 1 and 1 minus x are both 1 minus x, and the absolute value of x is minus x since x is negative, so that the sum of these two fractions is indeed 1. Therefore, z1, z2, z3, and z4 must satisfy the equation of the absolute values, and this completes the first part of the exercise. We now assume that this equation of the absolute values is true, and we prove that the four vertices lie on a circle. We had already seen that this equation is equivalent to this equation. We again use the Möbius transformation M, where M of z1 is 0, M of z2 is 1, and M of z3 is infinity. We set M of z4 equal to zeta, and we set zeta equal to x plus yi, where x and y are real numbers. This time we have to show that z4 is on the unique circle determined by z1, z2, and z3, and this is equivalent to showing that zeta is on the same isocline on which 0, 1, and infinity lie. That isocline is the extended real line. So we will have to show that zeta is a real number. Taking advantage of the invariance of the cross ratio under Möbius transformations, we replace z1 by 0, z2 by 1, z3 by infinity, and z4 by zeta. The fractions involving infinity both tend to 1 as z tends to infinity, so that we end up with this equation. Multiplying everything by the absolute value of 1 minus zeta, we get 1 plus the absolute value of zeta equals the absolute value of 1 minus zeta. The absolute value of zeta is equal to the square root of x squared plus y squared. And the absolute value of 1 minus zeta, or 1 minus x minus y times I, is the square root of the square of 1 minus x plus y squared. We square everything to get this equation. The square of 1 minus x is 1 minus 2x plus x squared. We simplify, leave the radical on the left side, and square one more time and simplify to get x squared plus y squared equals x squared. X squared cancels out. We get y equals 0, so that zeta is a real number, and zeta, or m of z4, lies on the extended real line, the isocline that contains 0, 1, and infinity. Therefore, their pre-images under M, which are z4, z1, z2, and z3 respectively, must also lie on an isocline which is either a circle or a line. Being the vertices of a quadrilateral, z1, z2, z3, and z4 have to be non-collinear, and therefore the isocline cannot be a straight line and has to be a circle. This completes the exercise.